Okay, today we're going to do 1.4 transformations. So if you haven't done your minds on already, do it please. And today what we're going to do is we're going to describe transformations that have been applied to a power function. So remember, a power function is just one term, it's a monomial. So y equals x squared is a power function, y equals x cubed is a power function. And we're going to be able to sketch the graph of that transformed power function. We'll also be able to come up with the domain and range, and we'll be able to state the vertex and the equation of the axis of symmetry of of any even degrees functions. So the other thing that we can do is we will be able to come up with an equation of a transformed function as well. Okay, let's get started. You know what? I don't have the minds on, so I'm just going to skip that for today, and we're going to go straight to the lesson. So, this is all review. Remember, everything you've learned about transformations applies to all functions, including power functions. So we have a power function x to the n, and we are saying we are transforming it in the same way you've always transformed functions. So you kind of use this as your little guide. Oopsie. And we know that the A is the vertical stretch or compression, the K is the horizontal stretch or compression, the D is the horizontal translation, and the C is the vertical translation. You know all that. So all this is saying is if you have an even degree, so n is an even number here, then we've got these parabola looking things. And remember, we talked about the order of the zero. Well, it's the same idea here. If this gets higher and higher, but still even, then this flattens out. But this point here is the vertex here and here. Of course, if it opens down, it's got a max. If it opens up, it's got a minimum. We know the range would be everything from here, including this y value on up to infinity, and from here it would be from this y value down to negative infinity. We'll do an example of that shortly. Okay, so those are our transformations applied to the graph of y equals x to the n, where n is any whole number. It says non-negative integer. Well, I apologize for that. I don't like that terminology because by definition, it should really be a whole number. Okay, an accurate sketch is obtained by applying A and K before C and D. Yes, the A and the K refer to the stretches and the reflections, and the C and the D are the translations, and we always do the multiplications, so the stretches and the reflections, before we do the additions. We must do it that way. And the easiest way to apply your transformations, I believe, is to go from left to right. So start with any reflections, stretches, and then the last two are always the translations. Okay. You know all these rules. I'm not going to go over them. A is the vertical stretch or compression, etc. We know all of this. The K is the big one because sometimes you have a little bit of difficulty with the K. The K is the value in the function already. So if we had something like this, I don't know. We know our K is 2, and then the stretch, the factor by which it is being stretched would be 1 over 2 in this case. And if it was being compressed, it would be by a factor. Sorry, I'm wrong. If K is 2, this would be a compression by a factor of 1 over K, which is 1 over 2. All right. The next thing I want to show you is this shortcut for figuring out your transformed points. So last year, what you did was you started with the key points of the base function and you applied the transformations one at a time, left to right, to come up with the final transformed points. And you had this chart with a bunch of rows in it because the points were changing as you applied each transformation. Well, this little formula here will give you the final x value if you start with an x value and you apply these parameters to the original point. And so you don't have to do all of the transformations one at a time. You can do them all at once. So that's what this is saying here. Okay, so we will do an example in a second, and you'll see what I mean by doing that. All right, so here we go. We're going to do it right now. It says, given a base function of y equals x to the fourth, state the parameters a, k, d, and c, and the corresponding transformations required. So a is -2. We're going to go with k is 1/3 right here. So whatever's here has to be in factored form, remember. So if it's not, you need to factor whatever number is outside the or is attached to the variable in order to get the correct horizontal translation. We've got d then is equal to the opposite sign of what's here, so d is -4 and c is -1. All right, let's describe the transformations one at a time, left to right. So the first thing is the negative, which is a reflection, of course, in the x-axis. Number 2, we've got a vertical stretch, and I allow you to use BAFO by a factor of 2. The third one is a horizontal. Now we have to think about this. Is it a stretch or a compression? So it is, if k is between 0 and 1, this is our k, then it's a stretch. So it's a horizontal stretch, BAFO, 1/k. So 1/1/3 is equivalent to 3. So this is a horizontal stretch by a factor of 3. Then we've got horizontal translation, left, oops, got to take the opposite sign. So left 4 units. And last but not least, we've got that vertical translation down 1 unit. Okay, so this should be fairly straightforward for you guys because you've done so much with transformations. Okay, now here's where we're going to use this little shortcut. Now again, I'm not making you use the shortcut. If you want to set up a chart and apply the transformations one at a time, you're absolutely free to do that. So the very first thing you would do, I think I'll just write the formulas here just so that I can have them at the ready. So let me just talk about the formatting. This is AY plus C. So it's got that little subscript N, and that just means we're going to use a variety of points. We're going to take all of the x values of all of the key points. So that's all that's indicating. And this one is just differentiating itself from this one. This means that we've got a new x value once we put in our old x and divide by k and add d. Okay, so that's just notation. Okay, so for the graph of y equals this mess, we know that the base function was y equals x to the fourth. Okay, that was our power function. And so we know that we can figure out the 5 key points to start with. So I'm going to start with -2 for my x, and when I put in -2 here, I can see that I'm going to get positive 16. When I put in -1, I can see that I'm going to get positive 1. When I put in 0, I'm going to get 0. When I put in 1, I'm also going to get 1, and when I put in 2, I'm going to get 16. Okay? So use those 5 key points for y equals x to the 4th. If this was y equals x cubed, you would use the same x values, and then you would just generate the corresponding y values for that. Okay, so change my pen color here. I'll just do one example maybe over here. So x primed is going to equal, if I take the -2 divided by, I should write in my a, my k, my c, my d, 2. So the a is -2, the k is 1/3, the d is -4, and the c is -1, right? Pick it out all out of that. So over here then we had -2 for our x value divided by k, which was 1/3, plus my d, which is plus really -4. So when we sort that all out, we get x primed. This is -6 when I flip this and multiply. -6 plus -4 is -10. So this -2 on our final transformed graph will be -10. I'm going to do the same thing for 16, but now I'm using the formula for y primed. So I'm going to say y primed equals a, which is -2, times my y, which is 16, and then plus my c, which is -1. And when we sort that out, we get -33. Okay, so -10, -33. Now we're just going to keep going. I'm going to ask you to try and do it with all of the other points. So just pause the video now, and I will crunch the numbers as well, but I won't show the calculations. I'm just thinking aloud here. This is going to be trying to do this in my head. Sorry, guys. But I put in 1. That's -1, -3. Okay. I did this in my head. Let's see if this graph looks symmetrical when we graph it. So if this is 2's, this is -10, 5, and -33. Oh, goodness, sorry. So -10, -33. Okay. -7, 1, 2, that's 6. There's -7 and -3. -4 and -1. and we've got negative 1 and negative 3. So, oopsie. So this should be symmetrical here. And last but not least, negative 5. So that's not right. So let's do that one again. 2 over 1/3 is 6. 6 minus 4 is negative, is positive 2. Okay. Hope you caught my error. So that's 2, and this should be negative 33 here. So 2, negative 33 is down here, and when we draw this, and it's difficult for me to draw this, so yours is going to look better than mine, I'm sure. Okay. Those are our, we put your arrows on and label 3 points, please, minimum, and include the vertex. So the vertex is negative 4, negative 1. Over here we've got negative 7, negative 3, and over here we've got negative 1 and negative 3. Okay, so if you like this method of using this shortcut formula, go ahead and use it. If you don't, apply the transformations one at a time. That's fine, but just know that it'll probably take you a little longer on a test. Okay, now it's asking us to state the domain and range. Just let me go back and make sure I've done, yeah, that was part, the third part. So state the domain and range of that function. Well, I know that the vertex, I'm not going to go back to it, but I know the vertex was at negative 4, negative 1. So that means that this was opening down and the maximum point was at negative 1. So for the domain of any quadratic function or even degree function, you're going to end up with negative infinity to infinity. And for the range, you're going to look at that max value of negative 1. And this is where you want to go from infinity, negative infinity, sorry, to negative 1. So you're coming, if you've got this thing, you're thinking, what's the smallest value up to my maximum value? Am I correct here? No, this should be a square bracket. Making all kinds of mistakes today. I'm sorry. So definitely a square bracket. It should be including that negative 1, right? All right. That's the domain and the range. The equation of the axis of symmetry is x equals negative 4. Of course, it's the x value of the vertex. Okay. Now it says, describe the transformations that must be applied to the power function y equals x to the 4th to obtain this transformed function. And the only reason I gave you this question was to just remind you that we can express transformations in 2 ways. We can give you the transformed function itself, and you can figure out what the base function was. In our previous case, that's what we did. In this case, what I'm doing is I'm telling you what the original base function was. It was a quartic. But then I'm giving you this sort of this map or this recipe that tells you all of the transformations. So this one, y equals negative f of 3x plus 2, is not a function. It doesn't give you the function. It's not the equation of the graph because it says f of 3x. It's got that f in it. And really what this is saying is take a function f of x and do all these things to it. So if I had to graph this just being given this, I wouldn't know what to graph. What was my original function? Was it a power function, with an even degree? Was it an exponential function? Who knows? So that's why we have to have both of these pieces in order to graph it. But for our purposes here, we could just state the transformations without knowing what the original function was. So if I just go left to right again, this negative is outside the f. That means it's pertaining to the reflection in the x-axis, right? It has to do with the y's. And the y's are the ones that are affected when we reflect in the x-axis. We go inside now. This is beside the x. This is our k value. So we know then that this is going to be a horizontal compression, BAFO, 1/3. Okay, it's 1 over K. And then the last thing is the vertical translation, because it's outside the function, up 2 units. Alrighty, that's it. That's all for that one. And last question. This was an easy lesson. We're being told we've got the power function y equals x cubed. That's our base function. It's been transformed. It's been transformed in a few ways, but what you have to do is only assume there's one stretch or compression, not both. Okay, so not a horizontal or a vertical, but just one of them, not both. So, sorry, that wasn't explained well. So only a horizontal or only a vertical, not both. The reason we do this, and I'm just going to do this as an aside, this isn't the equation of this function, but let's just say we had something like this. Y equals 8 times x minus 5 cubed plus 2. Well, that function can be expressed, that obviously just has a stretch, vertical stretch, not a horizontal one, because the k value is 1 here. So this one has a horizontal stretch, and that's the equation for a particular graph. But I could also write this. And that is the same graph, because we can manipulate this algebraically. First of all, we would have to factor out the 2 inside the brackets, but keep it inside the second set of brackets, because we haven't applied that 2 to the 3 yet. So when we do that, if we wanted to take the 2 outside the brackets, the second set of brackets, we could do that. We just have to apply the 2 to the third power. So we would say 2 to the 3, of course, is 8. That way we can take it out, and we end up with x minus 5 cubed plus 2, which is our original. So we can have horizontal, a horizontal compression. We can have a vertical stretch, and they will give us the same equation. And we can even have a combination of both of those. So that would be a little more complicated, where we might have a coefficient of a half here and then another number here. So we only ever tell you that there's one stretch, a vertical stretch, or one horizontal stretch. And we don't tell you which one, because you're free to pick. So what I would do for this question, is first of all, I would figure out where the turning, not the turning point was, but the 0 was for the original. You know that the original looked like this. That doesn't look very good. There we go. Not great on this tablet. This should have been here. That's y equals x cubed-ish. We know that this is at 0, 0. And we know that this point at 0, 0 is not going to be affected by vertical stretches or horizontal stretches or compressions, because when we multiply by 0, we still get 0. The only thing that is affected by the only thing that affects this point is the horizontal and vertical translations. So we know that if we can figure out which point this is in this, that we have the actual horizontal and vertical translations. So this looks like this point. It flattens out here and turns. So this was originally the 0. So we know that this has the x value is 3, so that would be our D, our horizontal translation right, 3 units, and our C, -4, which is our vertical translation down 4 units. So that's good. We have 2 parameters already. And let's just say, that we want to find, I'm going to make an arbitrary decision that I'm going to find an A value, which is the vertical stretch. You could have said, okay, I'm not going to find the vertical stretch, I'm going to find the horizontal stretch, and then you would have been looking for an unknown value K. Okay? But I prefer to use the vertical stretch. So what I'm going to start with here is I'm going to put in what I know already. I know that this is going to take the form A times x minus d cubed, because this was a cubic, they told us that's what we started with, plus c. So I'm going to sub in f of x equals A, I don't know yet, x is just part of my function, minus 3 cubed minus 4. So I can see I have an equation with one unknown, and so all I have to do is sub in my either point, not the point you already used, but either of these 2 points, or any point on the graph in fact, and you'll solve for A. So sub in 2, 4, and I will get 4 equals A times 2 minus 3 cubed minus 4, and then I'm just going to do some grade 9 algebra here and rearrange. Or I could just start by saying this is minus 1 cubed minus 4. I'll bring the minus 4 over to the other side. I get 8 equals negative A, so A equals negative 8. Awesome. So now I have enough information to say what is the equation. So that's f of x equals negative 8 times x minus 3 cubed minus 4 is a possible equation. And for those thinkers out there, if I asked you, oh, what's a different possible equation based on what I just told you, you would be able, if you wanted to get minus 8 out of something that was in here, you would have had to start with minus 2, because minus 2 cubed is minus 8. So I could have also had minus 2 here. Be careful, you can't just say minus 2x minus 3, because it has to be in factored form here. I'm just going to make those square. Sorry, that's messy. So that's a square bracket there. Cubed minus 4. So what we've got here is all the same transformations, except for now we have a horizontal compression by a factor of of a half, and we also have a reflection in the y-axis rather than a reflection in the x-axis. But this, if we double check, would generate the points that we have on the graph. If we substitute 4 in here, 4 minus 3 is 1. I'm missing a bracket there. 4 minus 3 is 1. 1 times negative 2 is negative 2. Negative 2 cubed is negative 8. So this whole thing is negative 8 minus 4 is negative 12. So we get back what we were expecting. So this would have been another possible equation had you chosen to solve for K. All right, that's it for the lesson. For those of you who weren't here, we do have a test next Wednesday. We're going to be reviewing Monday, Tuesday. I'll probably give you a little quiz on Monday. It doesn't count. It's just going to let you know where you're at. But right now, as of the weekend, I'm expecting that students will have all of the lessons done, 1.1 to 1.4. And I hope that you leadership kids can catch up as well. All right, good luck.